right, so we are ready to move on to our next unit, and we're going to be talking about circles. And with circles is going to come, we'll do area and circumference and stuff related to that later. But for right now, it's going to be angles that happen when you cross things inside circles, segments inside of circles and outside, and just some things that happen when different lines and segments interact with circles. Okay. So what we're talking about today is tangent lines. Now, I know we've heard that word before when we talked about in our last unit with trigonometry, that the tangent of an angle was opposite over adjacent. It's not that, so don't get them confused. They just happen to use the same word to talk about two different things. That sometimes happens in math. Okay, a tangent line is what we're going to look at today, and then some properties that go with it. So a tangent line is a line that intersects a circle at exactly one point. And that point is called the point of tangency. Okay, so in my diagram down here, I have this line intersecting the circle. Now it kind of looks like it's touching more than once here, but if you were able to zoom all the way in, like zoom all the way in, it's only going to touch at that one point. And so we say that the line AB is tangent to, now to name a circle, you literally just draw a circle, put the center in the middle, and then whatever the name of the center is what you call it. So AB is tangent to circle P at A. So in our diagram here, A would be the point of tangency. Okay? And then there's a theorem and then the reverse statement of the theorem. The theorem says if a line is tangent, so if this line is in fact tangent, then that line is perpendicular to the radius drawn to the point of tangency. So in other words, we all know that, remember, the radius is a segment from the center of the circle to the edge of the circle. So the radius in this diagram would be from P to A. So you could say PA or AP, whichever one. So this line is tangent because right here where they intersect, that is a right angle. And perpendicular means they cross to make right angles. So this is a perpendicular situation. So if we were going to state that out formally, we would say that the line AB is perpendicular. Well, that needs to connect. But perpendicular to the radius PA. And a radius is a segment, so I use the segment symbol there. Okay, so because this is a tangent line, we are able to say this. Now, the reverse of that statement, or in math we call it the converse, if a line is perpendicular to the radius at its endpoint on the circle. So in other words, if this intersection right here is 90 degrees, then the line is tangent. So then the line is tangent. So this converse is the reverse statement of what we just said up here. Okay, so if the intersection is a 90-degree angle, then we have a tangent line. Okay? Let's scoot this up a little bit. Okay, now what we're going to do is first thing we're going to do is we're going to determine if something is tangent to the circle. So we're going to be using this converse definition. So we're trying to determine if the line AB is tangent. So look at AB right here. You could extend it all the way if you want to, but A is the, oops, you can't see it. A is the point of tangency. Okay, and we have to determine if this line or piece of it is tangent to the circle. Okay, so actually we're using this one. If it is tangent, then this line is perpendicular to the radius. So in other words, where the line and the radius meet, we need a right angle. So our question is this a right angle? Right here. How do we figure that out? Well, if we think it's a right angle, then we would have just a right triangle right here. And what we learned in the last unit is that we can use the Pythagorean theorem to see if this is a right triangle or not. Okay? So we're going to use the Pythagorean theorem to see if the triangle is right. So if it is, if we end up with a right triangle, then we know it's tangent. If we don't get a right triangle, then it's not tangent. Okay, that's what we're going to look at. So let's make sure we have all the sides, because on these kind of problems, they're going to have you have to make sure you have every side of the triangle known. So this would be a leg, this section here labeled 8. And then we know that right here's a radius, so that's 7.5, but we don't know what this piece is. Because both of these together, let me draw it this way. Make that bigger. I need to know that whole length. Well, isn't this segment from the center to the edge, that's a radius by definition. And then if this radius is 7.5, that means this radius has to be 7.5. So then together, they're going to be 15. That's what you have to realize. They're going to give you a part of the side. You have to find the other one using the fact that it's a radius. And then add them together to get the whole length of the triangle. Or the side of the triangle, excuse me. So we got 8, 15, and we know this whole thing was 17. So now, which one do we let be c? Remember, Pythagorean theorem is a squared plus b squared equals c squared. Who do we let be c? It's going to be 17. So I'm actually going to write it with that backwards notation we did. So like 17 squared. And then we'll do 8 squared plus 15 squared. Remember, I got 15 from there was two 7.5s. They add together to make 15. Okay, 17 squared is 289. That's 64, and this is 225. So then 289. You add those together, and you also get 289. These are equal. Means that the triangle is a right triangle. So it is tangent. Let me say it this way. I put the line, but you really could use the segment if you wanted to, the segment symbol. Okay, so let me run through that again. We use the Pythagorean theorem reversely. We used it reversely to see if we have a right triangle. Because if we had a right triangle, then that means that angle is 90 degrees, and so it would be tangent based on this definition up here. If we don't get a right triangle, then we cannot say it's tangent. So I had to find this piece right here, knowing that that's also a radius, and all the radii in a circle are the same. So if this radius is 7.5, then this one is 7.5. You add them together, and you got 15. So 15 and 8 are the legs. They went over here. 17 was the hypotenuse, so I put it over here by itself in the C position. Then I simplified. They were equal. It's a right triangle, and so it's tangent. The line is tangent. Okay, let's do another one. So same exact process. let's see, I know this is 8. I know that's 15. They told me this outside section was 11. But notice that it goes along with that entire length right there. I need this other portion so that I know the entire length. Well, once again, notice that this portion is from the center to the edge. That's a radius. And this is also a radius right here from the center to the edge. So if this radius is 8, that forces this one to be 8. And then 8 and 11 together make 19. So our hypotenuse, right there, there's where our 90 would be. And here's our hypotenuse. So if this turns out to be a 90-degree angle, we have tangent. So we're going to set up just like we did over here. So 8 squared plus 15 squared. 19 squared is 361. 8 squared is 64. And then 15 squared is 225. And then 361. And then this ends up being 289. This is greater. So if you want to be technical, this would be an obtuse triangle. If this is anything but right, so if this turns out to be obtuse or acute, the line AB is not tangent. All right? Let's carry on. Oops. Okay, now we're going to find a side using this tangent to a circle definition. So find the segment indicated, assume that lines, which they'll tell you this every time. If it looks like it's tangent on this problem, it's tangent. We're just going to say it is. So this right here is on the exterior and it's touching one time. So this makes me a right angle, and this section labeled 9 would be my tangent line. So I want to know this entire length over here. How can I find that? We're going to use Pythagorean theorem again. So once again, and instead of, on this problem, instead of doing it the Pythagorean theorem this way, like this, we'll use it the way you're used to using it. So, okay, I'm rambling. Let me show you what I'm talking about. So once again, let's make sure we have every length we know or we need. So we've got this side is 9. Our hypotenuse is what we're trying to find. And then notice I have this section that's labeled 6 and the other section, I don't know what it is, or that's not labeled for me. I secretly know what it is because, once again, this is going from the center to the edge, making it a radius. And so this radius is 6. That means this is 6. And so together, we have a side of 12. So make sure you get the whole side, both pieces together. So now we'll do a squared plus b squared equals c squared. Remember, a and b are the legs, so it really doesn't matter who they are. So 9 squared plus 12 squared equals c squared. Remember, this is our c, we're trying to find it. 81 plus 144 equals c squared. 225, when you add them together, at this point you take the square root, and so you get that 15 equals c. Sorry, fiddling with the camera. Okay. So same thing. We'll use Pythagorean theorem. Let's make sure we have everything first, though. We're trying to find this side over here, so that would be a leg. So I'm going to call it A. If I'm trying to find a leg, I usually let it be the first one, but you can let it be B if you want to. You can let it be this one. I generally let it be this one. Now, notice again, they didn't tell you this side. Right here would be our right angle, sorry. There's the right angle. Remember where the tangent line touches the circle, that is where the 90 degree angle is at. I'm sorry. They didn't tell us this length because they're trying to get you to remember the definition of a radius. This goes from the center to the edge, making it a radius. And so this is also a radius. It's 3.6, so this one is 3.6. Now we have to make sure that we know that this whole length is what we need. So we'll add together 4.9 and 3.6, and that's going to be 8.5. And notice this is across from 90, so that makes this the hypotenuse. This value will be C. So we're going to do A squared plus 3.6 squared equals 8.5 squared. A squared plus 12.96, just type that in your calculator to get that, equals 72.25. Now we'll subtract. And A squared equals 59.29. Take the square root. And conveniently, this turns out to be nice and pretty at 7.7. We don't have to round or anything. Okay? Now these problems are really easy. These next two, I think they're very easy. So now we're going to find an angle inside. And so what we've got here is this is actually two different tangents, and then we have two radii because they go from the center to the edge. So we got two radii and two tangents. Those together, that shape makes us a quadrilateral shape, okay? And so we have to find this missing angle. They only gave us one of the angles. How are we going to find this one? We don't know the other two. Okay? That's a good question. So let's think back to what it means to be tangent. If this line is tangent to the circle, then the point where they meet is a 90-degree angle. That means both of those angles are 90 degrees. Okay, now we know what those are. How do we find the other one, the one with the question mark? This goes back way to Unit 1. In a quadrilateral, you should have learned that when you add up all the angles in any quadrilateral, any four-sided shape, it adds to 360. So all angles in a quad add to 360 degrees. You have to remember that for these problems. Okay, so we've got a four-sided shape here. If you want to be super technical about it, it's a kite, but anyway. You know three of the angles, and you're trying to find the fourth one. So we are simply going to take the total of 360, subtract the 90s, and then subtract the one they gave us. And when you figure that out, you end up at 102 degrees. That's literally it. You just you have to know that the total is 360 and that the two are 90, and that's literally it. Okay, same thing. These are 90. I like to draw those in. And so once again, we'll do 360 for the total, subtract both 90s, and then subtract the one they gave us. And then when you type that in, you should get 75 degrees. Okay, I'm just telling you right now, those are the two easiest problems on this entire thing, so you should not miss any of those on homework or a quiz or a test. You really shouldn't. Anyway, now we're going to look at a case where we have more than one tangent line. And so what's going to happen is a pretty neat relationship. It's very helpful. If you have two tangents and they both meet outside the circle at the same point, we kind of create a little bird here, if you can see it, like a little birdie shape. If they both tangents intersect outside the circle at the same point, this relationship happens. So the two segments tangent to a circle from a point outside the circle are congruent. So that makes this and that the same length. So they're both tangent, they come out here and meet the same point, and that forces them to be the same length. Okay? So we say that AB is congruent to CB. Okay, I don't like the way I drew my congruent symbol. Okay, now we're going to use that. So keep this in mind now for multiples. Both tangents are the same length when they meet outside. Okay? So again, we have the tangents meeting outside, we have some radii inside, and we are told expressions for both tangent lines. It says that when they meet outside, they're congruent. In other words, they're equal. So we're going to take 11x plus 2, set it equal to 10x minus 6. Or plus 6. I think I said minus 6. My bad. So then x plus 2 equals 6. Minus 2 minus 2. X equals 4. Okay? So on these problems, we're going to set the tangents equal. And look at this one. There's a little bit extra inside. See how they've got this segment connecting where the tangents intersect the circles? Ignore it. Don't even worry about it. You don't need it. All you need to know is what's written out here. Even if they write something in here, like they tell you a radius is 5, who cares? On this problem, you don't need it. You only work with the tangents outside. So we'll set them equal. 12x plus 2 equals 11x plus 5. Move the x. X is 3. Boom, there you go. Just like on the two angle problems a minute ago. You should not miss these, okay? These are really easy. You set them equal and solve for x. Couldn't be simpler. Now, this can get a little weird, so I'm going to try and explain it, especially on a problem like this. On this one, it's not that bad. What we've done now is we have what's called a circle inscribed in a polygon. So that means we've taken a circle, we stuck it inside a polygon, and it's going to touch that polygon at every side of the polygon will touch the circle one time. So in other words, it's going to create a bunch of little tangents. See that? And so what we need to do is we have to find the perimeter of this polygon. using this relationship up above that the tangents are equal. So let me explain it on this one, and then we'll go on this one a little bit slower because this one takes a little bit more brain power. All right, so they told you the length of one tangent for every side. Now, what I might do here is I might do some color coding. I think that might be helpful for us. If you want to color code, that's fine. You don't have to. Let me do this. Let me get some pens. Hang on. Okay. So, notice that the tangents have the same point. So they start from the same point and they spread out and touch the circle. Okay? So what I'm going to do is I'm going to color my tangents that are going to be congruent. So this right here, I'm highlighting it in red, or coloring it in red. They told me it was 13.4. Well, I know that if I come from this same point back down, that is supposed to be the same length. So I'm going to color it red again. And from my theorem, that is supposed to be 13.4. Those two are congruent. Okay? They told me that this one, that tangent piece was 13.6. I highlighted it in a lime green color. Well, it stops here, and then the new tangent starts and goes that way. So that means that it has to be congruent. So let's color it green. They go together. And if this one is 13.6, that makes this one 13.6. Okay. And now down here in purple, they told me that this one was 14. He shares with that tangent, and so that has to be 14. Now, notice we have every little piece of this outside triangle known. And so remember, perimeter is just you add up all the lengths around. So we'll add all these up. We have two 13.4s. We have two 13.6s. And then we have two 14s. So you add all that together and you end up at 82. And that's an easy one. Okay? What they will do sometimes is, like on this one, they will tell you a whole length on some sides. And then you essentially have to backtrack using this relationship, okay? All right, I'm gonna try and go a little bit slower on this one because this is the weirder of the two. So once again, I'm gonna do my color coding because it might help me. Okay, now I'm just gonna start here with the 5.9. Okay, so the 5.9 stops right here, and then it should come down to this one. So I'm gonna label that. I'm gonna color it red. Those two start from the same point and go those directions. So this piece right here is also supposed to be 5.9. I'm gonna go ahead and label that. On a problem like this, where you need multiples, that's a bad way to say that. Let me think how to say that. When you're trying to find the pieces you need, it's a good idea for one, color coding, and then labeling what they're supposed to be, because it will help you. Okay, and here's how it helps. So we just found that this portion that I colored red right here is supposed to be 5.9. It is a part of this entire segment from where it stops here and it continues on. That is all one segment with a length of 8.5. And so I need to find this little green segment right here. Okay? It belongs with the 8.5, but it's a different length than the 5.9. How do I get that green length? You simply subtract. Take the whole length, 8.5, subtract 5.9 from it. That ends up being 2.6. Okay? And then if he's 2.6, then that makes him 2.6. This little guy right here that I'm coloring. So he is also 2.6. Okay? Now, notice this time, the 2.6 in green is a portion of this entire length known as labeled with 9.9. I need to know how long this other piece is because that's going to help me get this one and then that one. So how long is this one going to be that I'm coloring in purple? Well, we'll take the whole length of 9.9 and subtract 2.6 from it, and that'll give us 7.3, which means that that one goes with him, and he is 7.3. Okay, now we've got this one over here. So obviously, these ones I'm coloring light blue will be the same length as well. But how do we find it now? We don't have anything to go with. We'll look up here. The red and the blue together make 13.9. See that? We know that the red portion is 5.9. I need the blue portion. And so just like we did over here and over here, we're going to take this whole length of 13.9 and subtract the red portion of 5.9. And that ends up being 8, which makes this portion 8. Okay? Notice how we had to do that. We had to find every little piece in here in order to find the pieces that we were missing to begin with. And all we did was just use that congruent relationship. So every piece that's labeled the same, that's colored the same thing, is the same length. And I labeled it appropriately. Now what we'll do is we'll add everything together. So to save yourself some writing time, use the whole length that they gave you. So instead of adding 5.9 plus 8, go ahead and use 13.9. So 13.9 plus this entire length of 8.5 plus this entire length of 9.9 plus, now here's where we have to do the pieces. So we got the purple 7.3 that we found right here, and then plus the blue, one of the blue 8s. Okay, it's this blue 8. This blue 8 was added in with the 13.9, so you don't have to add it back in. Now we'll add everybody together, and you end up with 47.6. Okay? So that wraps up tangent lines. It should be fairly straightforward. So remember in the beginning, we're going to use Pythagorean theorem. Let me refresh. Yeah, on the front, you use Pythagorean theorem to figure out if it's a right triangle or not, which tells you if it's tangent or not. Then you use Pythagorean theorem to find a piece of the triangle. And then we've used, how do I describe that? I'm trying to think. Oh, we end up with a quadrilateral. And you know that two of the angles are going to be 90, and they'll give you one of the other ones, and you have to find the fourth angle. So it's just 360 minus those three angles. And then it's this multiple tangent stuff. So that's all for tangent lines. So make sure to watch the video all the way through. And you'll have your homework assignment. I think there's just 20 problems. So it's not too bad. And as always, if you have questions, let me know.